In this video, I'm going to show you what electrophiles and nucleophiles are and how to identify them. In general, if you think about reactions in organic chemistry, they can be explained as interactions between electron-rich species and electron-deficient species. In organic chemistry, we call these electron-rich species as nucleophiles and the electron-deficient species as electrophiles. Now let's see how a given species can become either electron-rich or electron-deficient. Now you know the term electrophile is used to describe electron-deficient species. This part in this word phile. This in Greek it means loving. So the word electrophile means electron loving. Think about the charge of electrons. Electrons are negatively charged. That means electrophiles love negative charges. Then think about the general concepts you know about charges. Opposite charges attract. If electrophiles are attracted towards negative charges or electrons, that means the electrophile itself should be electron deficient or this electrophile should be a positive charge. Why the opposites attract? So some electrophiles can be positive charges. From your general chemistry, you know how you can get a positive charge. When something loses electrons, it becomes a positive charge. So positive charges are basically electron deficient species. For example, I'm taking H plus ion. So cation can be called as electrophiles. I'm taking another example. Now this one is a carbocation. I'm calling this as a carbocation. Why? You can see this positive charge on a carbon. So when we have a positive charge sitting on carbon, we call them as carbocations. So all positive charges can be identified as electrophiles. Why? They have a positive charge, so they can get attracted towards electrons. These species, they love electrons. What else can act as electrophiles? Partial positive charges. So what is the difference between a positive charge and a partial positive charge? You get a positive charge by complete loss of electrons. However, in partial positive charges, you don't find a complete loss of electrons. It arises from the bond polarities. For example, let's take this HBr bond. From your general chemistry, you know that there is a bond polarity in this HBr bond based on their electron negativity difference. The electronegativity difference results in this bond polarity you observe here. We denote these partial positive charges by using the symbol delta. So if you see a charge with the delta sign, that always implies you have a partial charge, not a full charge. Now in this given example HBr bond, what acts as electrophile is this positive end, the end that feels electron deficiency, not the whole bond. So what is the electrophile in this example? Not the whole thing, it's just this portion. This partially positively charged hydrogen is going to be your electrophile. Is there anything else that can be electrophile examples? Yes, incomplete octets. For example, I will take BH3. Now I'm going to show you the Lewis structure of BH3. You can see that there are only 6 electrons around boron. So this boron atom needs 2 more electrons to complete its octet. Because of that, we can call this boron as electron deficient. And because of that, this boron will seek for electron. This boron loves electrons because it has the ability to acquire 2 more electrons. So in that case, the incomplete octets can also be identified as electrophiles. Let's look at the nucleophiles. Nucleophiles are the electron-rich species. A phile means loving, and this nucleophile means it's nuclei loving. Now think about the nuclei of an atom. What do you find in the atomic nucleus? You have protons, and you know protons are positively charged. So that means basically the nuclei is a positively charged point. So why do these nucleophiles love nuclei? Nucleophiles are rich with electrons. Electron rich means that nucleophile itself is going to have a higher electron density or a negative charge. So the opposite charges attract, so these nucleophiles, they get attracted towards positive charges. Now let's see what kind of things that can become nucleophiles. Negative charges. Negative charges are electron rich. From your Gen Chem, you know how you get a negative charge. You get a negative charge when an atom or group of atoms acquire electrons. So having an excess amount of electrons than protons results in a negative charge. For example, these anions you see here, hydroxide ion or the chloride ion, these can be identified as nucleophiles. You can clearly see the negative charge indicating electron richness. What else can become nucleophiles? The lone pairs. Let's take some examples. Water molecule and this amine. In this water molecule, you can find 2 lone pairs. What does a lone pair means? The lone pair means the electrons that does not participate in a bond. If these electrons are not in a bond, that means they have some sort of freedom to get attracted towards a positive charge. So species that is going to hold lone pairs can act as nucleophiles. What else can act as nucleophiles? Multiple bonds. For example, double bonds and triple bonds. In order to show this electron richness in a multiple bond, I'm going to take some examples. Now I'm going to show you the Lewis structures for these given structures. These are our Lewis structures, and here you can see the double bond, and over here you can see the triple bond. Compare these multiple bonds with single bond. What does a single bond mean? What can you find in a single bond? Between 2 atoms, you have only 2 electrons. So a single bond means you have only 2 electrons between 2 atoms. But when it comes for the multiple bonds, you can find more than 2 electrons between 2 atoms. Here in this double bond, you can find 4 electrons between 2 atoms. In the case of triple bond, you can find 6 electrons between 2 atoms. So this means the electron density between these atoms is higher compared to a single bond. So when you have multiple bonds, the electron density in these multiple bonds is higher. That is why we call multiple bonds as electron rich. And also think how these multiple bonds are made. In multiple bonds, you find one sigma bond and pi bonds. When it comes for the double bond, you have one sigma and one pi bond. But in triple bond, you have one sigma and two pi bonds. So what exactly a pi bond? A pi bond results from partial overlap or the side-by-side overlap of p orbitals. So the electrons in these pi bonds are not very tightly held like the electrons in the sigma bond. And because of that, these electrons can actually get attracted towards a positive charge. So one reason is that in multiple bonds, you have larger number of electrons between two atoms, a higher electron density, and in addition to that, the pi electrons are loosely held. So those electrons can get attracted towards positive charge, making these multiple bonds into nucleophiles. Earlier I mentioned that reactions in organic chemistry can be explained as interactions between electron-rich species and electron-deficient species. Now I'm going to take a simple example, a reaction mechanism that you're going to find in organic chemistry, electrophilic addition reaction, to highlight this interaction between electron-rich species and electron-deficient species. Here I'm showing you an alkene. In alkenes, you find double bonds, and I mentioned double bonds can act as nucleophiles because there's a higher electron density over here. Now let's look into the electrophilic addition of HBr. From your general chemistry, you know that HBr can have this mentioned type of bond polarity due to the electronegativity differences. Now this is your electrophile. This electrophile and this nucleophile are attracted towards each other. So the electrons here get attracted towards this electrophile, resulting in a carbocation as shown here. And you can see how this hydrogen has been added. Now what this positive charge means is that we have another electrophile created. In the reaction medium, we are going to find the bromide ion. Now you can see a negative charge here. Now this is an electron-rich species. Now the reaction doesn't stop here. We have in between items this bromide ion and the carbocation. This carbocation is the electron deficient species which get attracted towards this bromide ion, which is the electron rich species. So we have another step in the mechanism, and you can see in the product this bromide has been added. And you don't see any charges in the final product. All the charges has been neutralized because the opposite ends got attracted to each other. So every time you come across organic chemistry mechanism, think about this basic and very simple concept. It's simply an interaction, or more like an attraction, between opposite charges. If you look into the organic reactions with this point of view, you will find reaction mechanisms much more easier and actually fun than you think.